All right, everybody. Hello, I'm Kushal Patel, and I'm a student at Saint Clair College, and I'm doing my post graduation. And we have here Agus Sudjianto. He is an executive vice president, head of model risk, and member management committee at Wells Fargo, where he is responsible for enterprise model risk management. Prior to his current position, Agus was the modeling and analytics director and chief model risk officer at Lloyd's Banking Group in United Kingdom. Before joining Lloyd's, he was executive and head of quantitative risk at Bank of America. Prior to his career in banking, he was the product design manager in the powertrain division of Ford Motor Company. August holds the US patent in both finance and engineering. He has published numerous technical papers and is co-author of Design and Modeling of Computer Experiments. His technical expertise and interests include quantitative risk, particularly credit risk modeling, machine learning, and computational statistics. He holds master's degree and doctor's degree in engineering and management from Wayne State University and Massachusetts Institute of Technology. So the platform is all yours, I
Thank,
guess.
thank you,
Okay,
Kushal.
let's.
Thank you for the kind introduction. So, hello everybody. Let me share my presentation here. So then I'll start my presentation. All right. My talk today is really talking about self-explanatory model. A lot of discussion, a lot of topic out there, a lot of research, as well as commercial product that talk about explainable AI, that talk about explainable machine learning. So today I'm going to share our view, particularly in the regulated entity, like banking. So we're going to make a differentiation between explainable model and self-explanatory model, and I'll share my view in terms of self-explanatory model. In financial institution like banks, we use model professively. We use model for financial model. That's a traditional area in banks like credit, market, liquidity, and so on. But we also use model for non-financial purpose. For example, for customer service, financial crime, marketing, compliance, etc. So from very mundane, when you make a phone call to banking center asking for replacement of your credit card, your voice will be listened by our machine learning model to help the customer service to answer your question, to all the way to stress testing how the company going to survive under the different stress conditions. So we are in the middle of COVID-19. That's a perfect example of that. Way before we bank had a lot of stress testing to look at the loss and revenue, how economic condition, economic stress will have impact to bank's balance sheet. When we use model very pervasively across the board. When we use model, of course we are exposed to what we call it as model risk. We believe that all model are wrong and model will fail. And when model fail, they create harms or to the institution or to customer. So either harm or unintended consequence, which can be financial harm if it's a financial model or non-financial harm. I'll give a few examples here. I'll go through very quickly. If a model is used for hedging in the capital market, the harm will be mishedging, and that create market risk. Financial crime to or conduct surveillance, model will fail to detect, so that create compliance risk. For staffing, we use model to do staffing, how many teller that we need to put banking. And if it's model wrong, customer will wait too long in the line. That's create reputational credit risk. It create credit approval. When model wrong, we approve loan that people that should not be approved. But it has also unintended consequence because model may create unintended consequence of fair lending issue. So treat customer with discrimination. So that's can create compliance risk. Even somewhat mundane model like online marketing. You go online, you get product offer, etc. It can create privacy and fairness issue because the data came from cookies, and the behavior of customer using surfing the web is very demographic. So we get exposed to privacy and fairness as well. So that's all the thing that we care about. So when we talk about model risk and the driver, it can be from the sources environment. That's the biggest one, right? Because model is applied in an environment where environment change. COVID-19 is a perfect example of that. We designed the model before COVID-19. COVID-19 hit, the model exposed under completely different environment. The environment can create the input data that's coming in. During the pandemic today, a FICO score. FICO is the credit score that the financial institution use. During the pandemic, all FICO score going up. So input can be problematic too as a source of model risk. Model parameters, and then in the machine learning, the hyperparameter tuning that create of that, and the choice of model. So typically, people when build a machine learning model focus on model performance, but that's something that is not complete, and it can be dangerous just simply looking at model performance. So we need to look at the error, because model will be wrong. We're looking at unintended consequence that model will create. So the focus of that, one of the thing is understanding how the model will be wrong. So this is where explainability, interpretability of model is very important. We need to understand, because of the complexity, to understand what are the source of failure. We really understand what the model does and how the model make decision. So outcome testing alone is not sufficient. A lot of people applying auto ML or building model, hyperparameter tuning, variable selection, just based on the outcome testing. And that can be very dangerous, because outcome testing alone is not enough. We need to look at whether the model is sound or not when making decision. Now, when we start talking about explainability or interpretability of machine learning, there are several ways that people do it. Probably the most popular techniques that's available out there, and a lot of research, a lot of the promotion from many vendor or many tool developer, post hoc explainability. This is a post hoc, a tool, auxiliary tool that we apply to black box model. So plethora of tools available out there like Lime, SHAP, BDP, and so on and so forth. Those are, we have a black box model, we have gradient boosting machine model, we have neural network model, then applying all this auxiliary tool to explain. That's what I call as post hoc explainability. Some other people do it through model distillation. So simplified model that can explain the decision of complex machine learning model. In all of these things, we have to be very careful. All of these tools are approximation. They are inexact, and they can be misleading. So applying post hoc explainability tool like Lime and SHAP can be dangerous if we are not very careful. Now, the other aspect that people can approach is, instead of using a auxiliary tool to a black box model, let's come up with self-explanatory model that inherently interpretable, model that is not a black box. And a lot of that available out there. If some of you interested in what we do, we have what we call it explainable neural network. And also we're going to talk a little bit today of that, and looking at the ReLU networks. How can we make ReLU network as not black box, but it's really truly a self-explanatory model. In high-stake environment, in a critical environment, if you have a choice, if I have a choice, I will use self-explanatory model. I am not going to do a black box model and apply post hoc interpretability. When you don't have to sacrifice in terms of self-explanation, why do we have to apply black box? Here's an example. Before we go to that, this is an example with explainer. Problem with the post hoc explainability. I give a few examples here. This is a very simple case, very simple study. We're looking at, we fit the model data. By the way, the data is data that is in scikit-learn. This is just for illustration, is the Boston housing data, the famous Boston housing data that's included in scikit-learn. So we just try this one, okay? Let's fit a ReLU network, ReLU deep network, and see what this explainer do. So we apply deep SHAP, kernel SHAP, apply Lime. Yeah, so we apply SHAP to different SHAP implementation. We apply Lime, and we do what we call it as Alasia. This is the tool that we built to really extract the. We'll talk about that a little bit later in the presentation. What this one is. For now, Alasia is the exact solution, the exact coefficient, the exact explanation. What's important. Alasia is the exact one. So we pick 3 example, 3 point in this situation, and compare it. Look at how deep SHAP, kernel SHAP, they can be very different, and Lime can be different, and all of those are different from Alasia. Okay, so you can see the inconsistency, and they are can be inconsistent, and they can be misleading or misinterpretation. So be very careful when using any post hoc interpretability tool, because they are approximation, they are not exact, they're based on sample. So all kind of problem that you potentially have. Because of that, we'll talk about the exact way how to do it, approaching it using self-explanatory model, so that we have exact interpretation without any auxiliary tool, any problem that we have with any post hoc tool. Before we go that, I give another simple example here. We apply, we fit the very simple toy problems to illustrate the problem. At the top is the equation, very simple linear equation with some interaction. We generate the data, the true data, and then we have the data, and then we train very simple network, 3 hidden layer, 10 neuron in each. Okay, when we measure the AUC of the model 0.8345 versus from the data 0.835 is very good. It's almost things. So when we look at the model, because we're going to talk about this later, that we can extract local linear model, exact local linear model from deep ReLU network. In this example, the deep ReLU network has 3,426 local linear model. 63%, 2,159 of them only have one observation. So local linear model and deep learning can be less reliable. So I give an example here on the plot on the right-hand side. So each dot, its circle is the coefficient from local linear model from deep learning. So I'm just plotting one coefficient here. It's the x6 at the top. Supposed to be the value is supposed to be minus 0.8, the green line. That's supposed to be the true value. If you look at what deep learning does, ReLU deep learning, when the 2,159 of them is single sample, that's the one at the bottom. Look at the coefficient is all over the place. As local linear model in deep learning has more sample, the estimation becoming a lot more reliable. So in fact, some of them, instead of negative minus 0.8, instead of negative, it gives you positive. So this is the real danger when we apply deep learning without understanding what inside. And when you apply interpretability tool, post hoc interpretability tool, you will not see all of this. But taking advantage of ReLU deep learning, we will be able to see this very clearly, which is the topic of the discussion today. I'm going to touch this one very briefly. There is things that call explainable neural network, how we constrain neural network so that it's really interpretable. The key is to modularize it and to apply sparsity constraint. Some of you that interested in, you can go to our archive paper. So if you go to archive.org and search under my last name, you should see the paper on explainable neural network. That you can see clear explanation of what the what the network is doing. So I'm not going to talk about this. I'm going too much. I'm going to concentrate on the deep ReLU network. So let's look at the deep ReLU network as interpretable model. This is, I give a simple illustration here. I have a 2-layer network, very small. The first layer have 2 neurons. The second layer has 4 neurons for illustrative purpose. And I constructed the weight in such a way that basically, depending on whether given the input data, neuron 1 can be on, neuron 2 off, or neuron 2 is off, neuron 1 is on, or both of 1 is on, or both are off. So in this example, the first layer is really partition the data into 4 partitions: 0, 0, none of them on; 0, 1, second one on, first one off; 1, 1, both of them on, both of them on. So and then the next layer, what's the next layer do? The next layer do is basically it partition further. Partition further the data from that into a smaller and smaller partition. So what the deep ReLU does is basically, with the deep ReLU network does is basically, the more layer, it will partition it into a smaller partition the data, so that locally linear model is the best. So that's what deep ReLU does. So segment it into a small segment, many different segments, and for each segment, deep ReLU has local linear model for that. And we'll go through that example in a little bit. Here is an example to illustrate the process, how the ReLU is a linear model. It's basically local linear model. So this is an example. I have a very simple x1 equal to 2 two-dimensional problem, x2 equal to 1, and this is the weight. Based on that weight, the first neuron output is 10. So 10 is bigger than 0, bigger than 2, because this is the weight. Bigger than on the bias, bigger than 2. So this node is on. When this one 0, smaller than 1, this one is 0, so it's off after putting the weight. This output is including the weight. 10 bigger than 0, so it's on. 0 is 0, so this is off. 1 is things is on. Going to the next layer, the output is 13 bigger than 0, so it's on. This is off. So if we trace every point in a train network, we trace every point in a network. Each point is associated with local linear model. We can get linear because it's on, it's linear. Going to the next one is linear, so it will be still linear. So when the neuron is on, the linear region is on, so we can get propagated. So any of you that interested in, you can go to more detail in my paper in archive.org as well. So go search in there the paper in archive.org, along with the package, Python package in GitHub that you can do to try. Basically, is what happened is deep network is a create activation pattern, where locally is a linear model. The network is partition the same data into small region, as I presented in the previous page, and locally it fit linear model. It's just, it can be so many of them. So in this, it can be a lot. It can be big number when we talk about local linear model, and some region will have a lot of sample. In this illustration, in this case, one region has almost 80% of the data, but other region at the bottom, very small data set. And in fact, many of them will have only single samples, just like the illustration that I showed before. Given the local linear model, given the partition, now we can get all the coefficient. We can plot the coefficient, so we can see on the bottom left of the figure here, it plotting all the coefficient of the local linear model. You can see how the local linear model vary from one to another. So we can look at, once we extract the local linear model, we can get exact interpretability, unlike LIME or SHARP, which is based on approximation or sampling. Here we get exact interpretability because we know we got exactly the linear model for each data point in the network. So we can plot it. For example, we can plot it using box plot for each variable. We can look at the box plot, how the coefficient for each variable look like. So you can see it here. It's non-monotonic because it's plus and minus. The coefficient is some positive, some of them negative. So you can see how sound the model is. If the coefficient should be monotonic, all of them should be positive, all of them should be negative. You can see it very, very clearly from the local linear model that you extract from deep ReLU. You can even simply plot it to look using simple parallel coordinate plot like the one in the bottom right corner. From that, you can calculate feature important exact because you can calculate exactly the feature importance, not approximation. We can look at the profile plot, how the model working in its area, and we can look at different region. We can see the equation very, 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 very exactly. Here is an example that I wanna put before I'm going to stop my presentation to for Q&A. I want to give a little bit time for question and answer. This is a simple example. I'm here using home lending data. We fit deep learning. The original DNN have so many local linear model, right? So we say, okay, let's control it because many of the local linear region we have very, very few sample. Even maybe only one sample. If we do it for classification, in this case, default on the default, it's one class problem. In many regions only have data from one class. So we need to simplify it, make it more reliable. So we regularize it. You can do apply regularization to reduce the number of local linear model without sacrificing the performance. So we can come up with simpler model through regularization or through pruning or through merging of the region. So you can read our paper on more detail on the merging. In this example, if you look at it simplified into 3 region only. We simplified through region only. We have region 0, 1, 2, 0, 1, and 2, call it at this point in time. If you look at the second table, the original ReLU DNN on the training side and on the testing side. If you look at the merging, so we reduce it into 3 region instead of 1,000 of region. The performance, the testing is not deteriorating. It's that you see the testing, it has the same performance. We can even simplify it further. What we call it, they call it flattening. From deep network, we can flatten it into a single layer network when applicable. In this situation, it's applicable. When we flatten it, it produces even improve the performance. The performance is better. So we can with this 3 region, then we can look at it. Really, the model, what you need is 3 linear equation, not 1,000 of them, 3 local linear equation, and we can diagnose how the data is partitioned by these 3 local linear region. In this case, is based on FICO score, credit score, FICO, and based on loan to value. You can see the distribution of loan to value and FICO in those 3 different region or 3 different segmentation, how they are different, and what are the linear model around that, what's significant, what variable are significant. If you look at the chart at the bottom left, bottom right, you can see on region 1 and region 0. Those are that's the how the what's the most important variable in there. So you can see the how FICO are important and how the LTV are important. So in this situation, we plotting FICO and LTV, and the left hand side is plotting the delinquency status. So model becoming extremely interpretable. It's self-explanatory. The model itself has the coefficient, has information that are explainable, unlike applying a post hoc interpretability tool that can be misleading. So let me put the last words, and I'm going to open it for Q&A. So sophisticated, interpretable, self-explanatory machine learning model are already available. In this presentation today, I show how we do deep ReLU network. We can make it very interpretable based on local linear model constructed by the deep ReLU. They can be regularized, reduced, can be simplified, the model. So we do not need the complication and flawed post hoc explainer. If we have have to explain the explainer, we are in trouble. And many of the explainer are not very easy to explain. So let me stop right here. And I would like to open it for question and answer. If you have any question, let me know. We have 10 minutes here to do Q&A. Kushal, you want
Yeah. So
to
yeah,
help?
we have three questions available. The one is from the Ajit. He's asking, can deep ReLU network scale to thousands of features with millions of instances? Will it be still interpretable for those cases?
Oh, absolutely, absolutely. So I think the key is you need to regularize it. If you the more you regularize it, it will be the more interpretable. So it's not, you need to understand. Of course, if I have, let's say, thousand of feature, okay, not all feature are important. Some of them are important than the other. So we want to look at what are the important features, right? So we can look at that, and then how many local linear model? Well, if I can get less number of local linear model with the same performance, in fact, that is a better way. In the example of home lending is an example of that. You know, the data is very simple, so you don't really need thousands of local linear model. If you train deep network very simply by using early stopping, you'll end up with 1,000 local linear model, and you don't need that. So you can, if you apply regularization, let's say with L1 penalty, it will be much less. Even with dropout, you will have much less number of local linear model. And that can be analyzed through the tool that we put in GitHub. It's called Alasia. We have the tool that you can analyze the complexity of the model.
We have next question. That is, any trade-offs of using self-explanatory models? For instance, is it much more demanding computationally?
It's not. The thing is, uh, depend on, of course, yeah, like if you compare a GPM and deep learning is more involved to train than GPM, right? GPM is probably easier, simpler to train. Deep learning is computationally is more. But if you compare deep learning and deep learning, it's a matter of really regularization or merging some of the regions. So if you guys, it's the same. If you do a deep learning, it's the same computation. It's just you need to apply proper regularization. But if you compare with XGBoost and deep learning, of course, deep learning will be computationally more demanding. But the thing that I'm giving example here is you can apply ReLU deep learning.
All right, and the one last question is from Ali. That is the code for your work on LimeSub publicly available?
The all the Lime and Sharp, the comparison of Lime and Sharp, we have not published that, but you can see a lot of publication out there already. The problem with Sharp, the problem with Lime. So a lot of many papers talk about the problem with Lime and Sharp today. So Google it. There are plenty of paper in archive that talk about problem with Lime and Sharp.
All right. So I guess we have one more question. Okay, yeah. This is from Ram. When you say use regularization in deep learning, is this what
Mhm.
you mean? Using something like TF Keras regularizer, TensorFlow Core V2.4.1? Can you help?
Yeah, there are many regularization techniques. Yeah, let me say this one. If you do regularization, right? If you train neural network today, there are the common techniques today are three things, right? You do early stopping. That's so that you will not overfit. That's some kind of regularization because so that it won't overfit. But it unfortunately it create too many local linear model. Okay. So the second thing is people do drop out. This is already in Keras and TensorFlow. It has this one as well, right? So you can do drop out because it's randomly dropping off neuron. It helps reducing the number of local linear model, control the overfitting and reducing local linear model, but still too many. Too many local linear model with dropout. The third thing that you can do is doing the regularization using L2 or L1 penalty. L2 is known as weight decay when you train a neural network, right? Or using L1. This is in TensorFlow, this is in Keras, this is in scikit-learn as well. So you can apply L1 penalty. The problem with L1 penalty, if it's too much, the performance is degrading. Okay, so the trick is you need to search your hyperparameter so that the performance is not degrading, the number of local linear model is small, you stop. So in combination using that and using the Alicia tool that is in the GitHub, so you can download that tool, combination of that. In the paper that we wrote in arXiv, we adding one more techniques that we call it as region merging. So you can do region merging. So typically what we do, we penalize it, but not too much on the regularization so that performance is not degrading. Then you do region merging, because region merging doesn't deteriorate, not deteriorating performance dramatically, unlike the L1 penalty. So check the paper in archive.org, search under my last name. You will see that unwrapping the black box of ReLU DNN, and then follow the link, go to the GitHub, download the tool. The tool is there, so you can try all the experiment that we show in the paper and do everything yourself. So the code is available out there to get all the local linear model, to get the to make ReLU as to get all the local linear model from ReLU. You can. It's very simple idea. You can do it yourself too to do it, but we just put it out there. The computation make it available. It has all the plotting, charting to analyze all the local linear model from the deep network. So go ahead and try it.
All right. So that was a very good talk, and thank you so much, Agus, for the very good session. And it was really knowledgeable. Even I could understand a bit about it. Yeah. So thank you.
Thank you so much. Thank you, everybody.
All right. Have a good day.